Soon we're going to be solving quadratic equations. The solutions to quadratic equations often involve square roots. So in this video, we're going to be reviewing how you simplify square roots. So let's jump in. The directions will be simplify, and the first example will be the square root of 20. Now we're looking for any perfect square factors that are a part of the radicand. Remember the vocabulary? The symbol right here is called the radical sign, and the number or expression under the radical sign is called the radicand. So in this case, our radicand is 20, and we're thinking about our perfect squares like 4, 9, 16, 25, and we know that 20 is 4 times 5. So we can rewrite that radical as the square root of 4 times 5. But we can separate that into two separate radicals, the square root of 4 times the square root of 5. And when we simplify the square root of 4, we get 2. So our answer is just 2 square root of 5. And now notice our radicand does not contain a perfect square factor. So let's do another one. Let's let the next one be the square root of 700. And again, my mind is going through the perfect squares that we know. 4, 9, 16, numbers like 81 or 49. But in particular, right here with this 700, do you recognize 100 as a perfect square? So 700 is 7 times 100. So I have a nice perfect square right here. Now, in the previous problem, I took an intermediate step right here and separated them. We don't actually have to do that. Let's just bring out our square root of 100. We know that's equal to 10. So we'll say the answer to this one is 10 times the square root of 7. And this one's complete. Let's simplify another one. This example will be 10 times the square root of 18. Our radicand is 18, and I'm thinking about any perfect square that is a factor of 18. So again, my mind is thinking about a 4, a 9, a 16, a 25, those types of numbers. So I know 18 is 9 times 2. So I have 10 times the square root of 9 times 2. Here's my perfect square sitting right here. So the square root of 9 is 3. It comes out and is multiplied by the 10. So I have 10 times 3, that's 30. And the square root of 2 stays underneath, or the 2 stays underneath the radical sign. Let's look at this problem. The negative square root of 36. The coefficient of this radical is just this negative 1 sitting in front of the square root of 36. You don't see the 1, but we know it's there. So we can still just simplify the radical, and we know the square root of 36 is just 6. So our simplified answer would just be negative 6, and there's nothing more to it. But let's look at this next one. It's the square root of negative 25. remember that we can't square a real number and get a negative value. And that's why we're going to the non-real numbers. Do you remember this? Do you remember that? I'm coming over here and as a little aside, that I is our imaginary unit, and we define it such that I squared equals -1, or we think of I as equal to the square root of -1. So when I'm looking at the square root of -25, I'm going to think of that as the square root of -1 times 25. So this square root of -1 is equal to I. So I have I times the square root of 25. Now we simplify the square root of 25 the same way we normally do. The square root of 25 is 5, so our result is 5I. So this is a non-real number, but it's still a totally legitimate answer to what's the square root of -25. So let's do another one where the radicand is not positive. Let's let it be the square root of -10. And again, we have a negative underneath the radical sign. So we have -1 times 10. Again, we can take the square root of -1 and rewrite that as I. This time, our radicand is a 10. There's no perfect square factor in 10, so this one is simplified. Now, as we practice more of these, you don't necessarily need to go through that intermediate step right here. You'll start to see them, or maybe you already do. So if you had the square root of -49, for example, it's totally okay to go right to 7I. So remember, anytime you have a negative underneath the square root sign, our answer is going to involve I. Let's keep going. Here's our next example. It will be 5 times the square root of -12, and our job is to simplify. So we recognize that there's a negative underneath that square root, so I know an I is going to be involved. I know that 12 is 4 times 3, so I'm thinking this. I have a -1 times a 4 times a 3. I can take out the I because of this square root of -1. I can take a 2 out because of the square root of 4. So when I bring out the I and the 2, I would have 10I times the square root of 3, and it's complete. And with practice, you won't need to go through that intermediate step at all. For example, suppose we have 6 times the square root of 44. Depending on how much you have practiced these lately, you may or may not be able to get right to the answer in one step. Let's try it. I'm looking at the square root of 44. I'm thinking about my perfect squares, so I know 44 is 4 times 11. So when we take the square root of 4, out comes a 2. It gets multiplied by the 6, and we have 12, and the 11 stays underneath. But if you're thinking, oh no, I need to write out my more detail, then go ahead. Write your 6 square root of 44 as 6 times the square root of 4 times 11. And you can even take another step and write it as 6 times 2 times the square root of 11. And there's your 12 square root of 11. I'm just saying that it depends on where you are. If you are comfortable now just going straight to this right here, that's totally fine. If you haven't practiced these for a while and you need to take these 3 steps, that's okay too. Let's continue. Let's look at this one. We'll let it be 7 times the square root of 72. Often when people are simplifying the square root of 72, they think of 72 as 9 times 8. Nothing wrong with that. I'm going to write out all the details so you can see it. So we have the 7 out front, and we have 9 times 8 underneath the radical sign. Our 9 is a perfect square, so the square root of 9 is 3, so the 3 comes out and gets multiplied by that 7. So we have 21 times the square root of 8. Often people aren't careful here, and they just think they're done, but notice the 8. The 8 is not a perfect, it is not, well, it does involve a perfect square factor, so we need to simplify that. We know that 8 is 4 times 2. So this radical is not simplified. We need to bring out more. So if we bring out the square root of 4, which is 2, we multiply it by the 21, and we would have 42 square root of 2. And it's complete. Now, someone else could have looked at the problem differently. Maybe you were thinking this when I was writing down the problem. Whoops, and let me back up just a little bit. And that's not 20. We'll write that again. 7 square root of 72. Maybe you thought of 72 right away as 36 times 2. And if you did that, you get to the answer quicker. So we have 7 times 6. That's 42 with the square root of 2 left. But it doesn't matter as long as you keep breaking down the radicals or the radicand and determine that you have a perfect square present, or you determine that there isn't a perfect square present, you'll be fine. You just need to make sure you keep going until there is no perfect square factor. Sometimes we see a problem like this. I'll make it a basic one, the square root of 50. And people just see it as 5 times 10. Suppose that's you. All I see is 5 times 10. Let's write it as 5 times 10, even though neither of those is a perfect square. But now I see I have a 10 underneath that radical sign. I could break that up more. 10 is 5 times 2. So in fact, I would have 5 times 5 times 2. And now look, we have this, a pair of factors that are the same. And anytime you have a pair, they are a perfect square. That's really a 25. So we can take the square root of that 25 and bring out a 5, and we'll have the square root of 2 left. So the idea of prime factoring is a strategy I use if the number looks ugly or I just don't see the perfect square factor. I can prime factor and then look to see what I can bring out. Just to be clear, it was unnecessary to prime factor if, right, we'll just say or, if you notice that the square root of 50 is 25 times 2, you could have just gotten to the 5 square root of 2 that way as well. Now I want to talk about how we rationalize the denominator of an expression with a square root in it. So the directions will be rationalize the denominator, and we'll start with this expression. I'll let it be 5 over the square root of 2. And by rationalize the denominator, it means we're going to find an equivalent fraction to this that has a rational denominator instead of an irrational one. Right here, the square root of 2 is irrational. Remember, though, when you're trying to find an equivalent fraction, you really only can do one thing, and that is multiply by 1. That's it. If you multiply by something besides the number 1, you will be changing the value of the number. But remember, 1 has lots of different looks. 1 equals 6 over 6, or 5 over 5, or 123 over 123, or square root of 11 over square root of 11, or most important for this problem, it's equal to the square root of 2 over square root of 2. So anytime we want to, we can multiply a fraction by 1 in any of these forms. So I'm going to multiply by 1 in the form of square root of 2 over the square root of 2. So let's do that. I'm still looking at this problem, 5 over the square root of 2. And I'm going to choose to multiply it by square root of 2 over the square root of 2. Now in the numerator, 5 times the square root of 2 is just 5 square root of 2. But in the denominator, I have square root of 2 times the square root of 2. That's the square root, that's the square root of 4. But the square root of 4 is just 2. And now look at my denominator. It's a rational number. So I have met the requirement for the directions. It says to rationalize the denominator. So this one is done. Let's do another one. We'll rationalize the denominator with 14 over the square root of 7. So remember, we can only multiply by 1 to rationalize the denominator, but I want to multiply by 1 in the form of square root of 7 over square root of 7 this time. In other words, I'm trying to build a perfect square underneath the radical sign in the denominator. So in the numerator, I have 14 times the square root of 7. In the denominator, I have square root of 7 times square root of 7, which is the square root of 49, but I might as well just write that as 7. One last point to make on this one is this is not simplified because it is reducible. The directions don't have to say reduce. You know you should always present your answers in simplified form. So let's do the reducing. The 7 in the denominator and the 14 in the numerator have a common factor of 7. So let's do the canceling. 7 goes into 7 once. 7 goes into 14 twice. And that means we have 2 times the square root of 7 as our simplified result. And notice the denominator is rational. The denominator right here, you don't see it because the denominator right here is this 1. We just don't write it down here. Let's do a couple more. Let's rationalize the denominator on this problem. It will be the square root of 3 over the square root of 5. Do you recognize what we need to multiply by? We're going to multiply by 1 in the form of the square root of 5 over the square root of 5. That will build that perfect square in the denominator. All right, well, let's go to the denominator first. Square root of 5 times square root of 5 is just 5. And in the numerator, this time we have 2 numbers underneath radical signs, so we'll just multiply those radicands together. So square root of 3 times square root of 5 is square root of 15. And this one is complete. Notice it is not reducible. because the coefficient in front of that square root of 15 is a 1. And the 1 and the 5 would not reduce. I don't really need to keep that 1 there. I just wanted to point that out. Let's do one last problem. The directions are still rationalize the denominator, and we'll now look at the square root of 8/3. Remember, when you have a radical sign that covers an entire fraction, we can separate it into two separate radicals. So I'm going to rewrite that as the square root of 8 over the square root of 3. Now, before I multiply by the square root of 3 over the square root of 3 to rationalize the denominator, let me simplify that numerator. You see that square root of 8, we know 8 is 4 times 2, so out will come a 2. 2 square root of 2. And I still have that square root of 3 in the denominator. Now we'll multiply by square root of 3 over the square root of 3. And we multiply straight across. So in the numerator, notice we have square root of 2 times square root of 3. That's the square root of 6. And we just have 2 times 1, those coefficients. This 2 and this 1 would just give us the 2 in front. In the denominator, we have square root of 3 times the square root of 3, and that is just 3. This one also is not reducible because the 2 and the 3 don't have anything in common. So these were just a few basic problems so that when you get to results like this at the end of solving a quadratic equation, you'll be able to simplify those expressions.